The new pictures gained by the James Webb Space Telescope have left scientists dumbfounded, uncovering an unanticipated reality about the universe. As opposed to just widening our view of the universe, these pictures have revealed a perturbing truth. Our current understanding is lacking. To comprehend the immense potential outcomes of the universe in its beginning phases, current hypotheses regarding the universe's origin are nearing their limits, prompting the need to revisit and investigate alternative speculations concerning its development. This situation leads to a significant question: how did the universe form, and why? These discoveries are bewildering even the most experienced experts in space studies. Thus, there is an urgent need to delve deeper into the true nature of the Big Bang and its ever-evolving intricacies. It may now be necessary to reconsider the Big Bang theory itself, as it has often been misunderstood in popular discourse. The Big Bang was not merely an explosion in pre-existing space. Rather, it marked the commencement of space itself, occurring approximately 13.8 billion years ago alongside the creation of matter and time. A fundamental concept in physics and cosmology is the singularity, a point where gravitational forces become so intense that space-time curvature becomes infinite. Billions of years after the universe's formation, we now observe our cosmic abode as part of an expansive and interconnected structure. For researchers, this highlights a critical aspect of the universe's persistence, emphasizing its continuous expansion. The universe does not merely drift into pre-existing space. Instead, space itself continues to grow. As earlier theories proposed, the first stars are believed to have emitted light roughly 200 to 300 million years after the Big Bang, marking the end of the so-called dark age of the universe. During this period, the first bright celestial bodies began to coalesce, ultimately forming mature galaxies. However, the rate at which these galaxies developed remains an unresolved mystery. A significant breakthrough occurred on July 22nd, when the James Webb Space Telescope revealed its first set of images, showing several galaxies, some of which were already in existence around 300 million years after the universe's birth. Although these galaxies were far younger than those observed today, they were noticeably smaller and less massive, consistent with scientific models of the time. The discovery began with 6 remarkable redshifted, bright spots detected by the telescope, triggering one of the most critical cosmic puzzles of recent times. These newly found galaxies, despite being similar in age to previously recorded ones, appeared nearly as large as our Milky Way. This revelation has sparked intense interest in the field of Big Bang cosmology. After examining a series of images captured by the telescope's near-infrared camera, scientists confirmed the existence of these distant galaxies using redshift data to verify that their light had traveled for over 1 billion years before reaching Earth. Consequently, these galaxies were already present between 570 and 700 million years after the Big Bang. This extraordinary discovery challenges conventional cosmological assumptions, which predicted the formation of much smaller and less developed galaxies during this early period. Surprisingly, the James Webb Telescope unveiled galaxies almost as massive as the Milky Way, defying prior expectations. Stars within these galaxies, bound together by gravity, had already accumulated mass surpassing 10 billion times that of the Sun. One such galaxy even showed signs of a mass exceeding 10 billion solar masses. However, whether this estimation is entirely accurate remains uncertain. Regardless, if this assumption holds, the matter density in the early universe would have been significantly higher than previously estimated, raising further profound questions. The discovery challenges nearly all conventional cosmological theories. Even if just one of these galaxies is verified, it would compel us to rethink our earlier beliefs about the formation of these early large structures. The matter density in the early universe would need to be much greater than initially calculated. An alternative explanation could be that these galaxies formed in a way entirely new to us. These findings are prompting scientists to reconsider the Big Bang theory. Many space experts express frustration over these discoveries, often voicing their concerns in scientific publications. Those challenging current models are frequently labeled as unconventional or extreme. Nonetheless, even the staunchest defenders of the Big Bang Theory are grappling with unresolved questions. These inquiries include fundamental issues, such as how something could arise from nothing 13.8 billion years ago. Was there a catalyst for this event, or did it happen randomly? Stephen Hawking famously argued that the concept of time, as we understand it, began with the Big Bang. This suggests that the process could not have been initiated by any external force or triggered by another event. Similar uncertainties surround the uniformity of radiation and matter across the universe. No matter where we look or at what distance we observe, there is a nearly identical distribution of systems, clouds, and radiation across the cosmos. Contemporary scientists explain this phenomenon using the theory of cosmic inflation. Other researchers have expanded on this idea, suggesting that the universe expanded in a more turbulent way. According to this perspective, expansion occurred only in specific regions like bubbles, while other areas continued to grow indefinitely. This model presents the intriguing possibility that other universes could exist within these expanding bubbles, each governed by its own set of physical laws. This perspective implies that our universe might not be the entirety of existence, but rather a component of a far more complex and vast structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe is proposed. However, this is not the only cosmological perspective. For example, an article published in NASA's spin-off magazine in 1955 suggested that the universe might never have had a Big Bang and that it has existed infinitely, possibly for an eternal duration. In this interpretation, the expansion of the universe would be non-existent, with matter gradually forming over time, creating the impression of slow, continuous evolution. One of the most fascinating theories emerges from quantum physics and string theory. Some studies have indicated that our universe and everything within it could be a projection or simulation originating from a higher dimensional reality. While this might sound like the premise of a science fiction narrative, it shares connections with the Kardashev scale, which measures a civilization's energy usage by its ability to harness the power of an entire galaxy. If a Type 3 civilization existed, capable of utilizing all of a galaxy's energy, it could theoretically create a perfect simulation of a universe. However, validating this scenario presents significant challenges. Delving into the depths of cosmology and the origins of the universe takes us into a realm of profound mystery and relentless scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of existence, challenging established models and urging scientists to reassess fundamental aspects of our understanding. At the core of these discussions lies the hypothesis of the universe's origin, which forms the foundation of modern cosmology. According to this hypothesis, approximately 13.8 billion years ago, the universe emerged from a hot, dense state, expanding rapidly to create the space-time and matter we observe today. This remarkable event was not simply an explosion within pre-existing space. It also marked the birth of space itself. The concept of a singularity, where gravitational forces become so immense that space-time curvature becomes infinite, supports our understanding of this initial stage of the universe. However, the discovery of massive, mature galaxies just a few 100 million years after the Big Bang challenges conventional ideas about how quickly the first structures could form. These findings suggest that the early universe contained a far higher density of matter than previously thought, raising important questions about how such significant structures could have developed so rapidly. This compels cosmologists to re-examine how galaxies like those observed by the James Webb Space Telescope came into existence shortly after the universe's birth. A key theory arising from these revelations is cosmic inflation, which posits that the universe expanded exponentially during the first moments following the Big Bang. This rapid inflation is thought to explain the uniformity of the cosmic microwave background radiation observed today. However, recent discoveries complicate our understanding of the early universe's evolution, suggesting that inflationary models may need revision. The growth of these early massive galaxies also prompts critical questions about the roles of dark matter and dark energy, two mysterious substances that constitute most of the universe's mass and energy. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, and dark energy drives the universe's accelerated expansion, their exact properties remain elusive. These discoveries are not only rewriting the narrative of the universe's origin, but also expanding our imagination regarding the nature of existence itself. For instance, some theorists propose that our universe might be one of many in a vast multiverse, where different regions of space could operate under distinct physical laws. Other bold theories, emerging from quantum physics and string theory, suggest that our universe could be a holographic projection of a higher dimensional reality. This idea, while speculative, resonates with ongoing efforts to reconcile quantum mechanics and general relativity, two foundational but seemingly incompatible pillars of modern physics. These groundbreaking discoveries underscore the profound interconnectedness between theoretical physics, observational astronomy, and cosmology. As the James Webb Space Telescope continues to unveil new data, it not only pushes the boundaries of scientific knowledge, but also challenges humanity's understanding of its place in the cosmos. The implications of these findings are vast. They compel scientists to revisit long-standing assumptions, question prevailing models, and explore alternative hypotheses. With each new revelation, we are reminded that the universe remains an enigmatic and ever-evolving frontier, filled with mysteries waiting to be unraveled. Remarkable arrangement of actual regulations. These ideas arising out of string hypothesis and quantum cosmology present an undeniably more perplexing and interconnected universe than recently considered. One such speculation acquiring prevalence is that of immortal expansion, in which universes are unendingly created within a larger expanding space. This suggests that our universe could be one among a boundless number of others, each with distinct physical attributes. The challenge, however, lies in securing observational evidence to support these theoretical hypotheses as they extend the limits of what can be tested through scientific means. Another provocative idea suggests that our universe could exist inside a computer-generated simulation, drawing comparisons to advancements in artificial intelligence and computational science, where simulations can replicate complex systems. If this idea proves valid, it would fundamentally alter our perception of reality and raise significant philosophical and scientific questions regarding the nature of existence itself. As observational astronomy progresses, instruments like the James Webb Space Telescope, with its unmatched sensitivity and resolution, promise to uncover significantly more of the universe's secrets. Future observations might provide deeper insights into the universe's earliest moments, potentially offering clues about its ultimate fate and the core principles governing its ongoing development. Meanwhile, particle physicists remain dedicated to unraveling the fundamental particles and forces that shape the universe. The quest for unifying gravity with the other three major forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal in theoretical physics. In the field of quantum mechanics, debates continue about the nature of time itself, with some theories suggesting that time could evolve or behave differently at more fundamental levels. Understanding the true nature of time within the context of cosmology could revolutionize our comprehension of the universe's origins and evolution. Moreover, the pursuit of extraterrestrial life continues to captivate both public interest and scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions beyond Earth. Future missions, such as the James Webb Space Telescope's exploration of exoplanet atmospheres, could reveal biosignatures pointing to life beyond our planet. As scientific exploration advances, philosophical investigations into humanity's place in the universe intensify. The search for answers to questions about existence, the likelihood of intelligent life elsewhere, and humanity's future in space exploration will remain integral to discussions across both scientific and philosophical fields. As scientific progress continues, the questions surrounding the origins and nature of the universe become more pressing. Discoveries made by the James Webb Space Telescope have highlighted the need for new approaches to understanding the universe. While traditional models of the universe's evolution have been foundational to cosmology, recent findings have challenged these ideas and opened the door for new paradigms. These discoveries suggest that our understanding of the universe's history and structure may need to undergo a fundamental shift, one that embraces the complexity and uncertainty inherent in the cosmos. Cosmologists are now tasked with revisiting their assumptions about the Big Bang and its aftermath. The idea that the universe began as a singular explosive event in a state of infinite density is still widely accepted. However, new data raises serious questions about the accuracy and completeness of this model. The discovery of massive galaxies in the early stages of the universe suggests that the process of galaxy formation may have been much faster and more efficient than previously thought. This has led to a re-evaluation of how galaxies form and evolve, with researchers proposing new mechanisms that could explain the rapid development of early cosmic structures. One such speculation involves the role of dark matter and dark energy in galaxy formation. Dark matter, thought to exert a gravitational influence on visible matter, may have played a significant role in shaping the structure of early galaxies. However, the exact properties of dark matter remain elusive, and its behavior in the early universe is still poorly understood. Similarly, dark energy, responsible for the accelerated expansion of the universe, may have contributed to the rapid development of galaxies and other cosmic structures. Another area of inquiry is the role of cosmic inflation in shaping the universe's large-scale structure. The theory of cosmic inflation suggests that the universe expanded exponentially in the first moments following the Big Bang, leading to the uniformity observed in the cosmic microwave background radiation. However, recent observations, including those made by the James Webb Space Telescope, have raised questions about the validity of this theory. Some researchers now believe that inflation may not have been a smooth, uniform process, and that local fluctuations may have influenced the formation of galaxies and other structures in the early universe. These emerging questions underscore the need for a more nuanced understanding of the universe's origins. While traditional models like the Big Bang theory have provided a solid foundation for cosmology, the new data is driving scientists to reconsider many of their long-held beliefs. This is no easy task, as the implications of these discoveries challenge some of the most fundamental principles of physics. Nevertheless, the pursuit of answers to these questions is essential for advancing our understanding of the universe. In addition to revisiting established cosmological models, these discoveries are also prompting new avenues of inquiry into the fundamental nature of space and time. The concept of space-time, which has been a cornerstone of our understanding of gravity and the behavior of matter, is now being scrutinized more critically. The possibility that space-time itself may be more dynamic and flexible than previously thought is gaining traction, with some theories suggesting that space-time could be subject to changes that are not yet fully understood. As scientists continue to probe the mysteries of the early universe, they're also looking to other fields of study for insights. Quantum mechanics, which governs the behavior of particles on the smallest scales, may hold the key to understanding the fundamental forces that shaped the universe's evolution. The relationship between quantum physics and general relativity, Einstein's theory of gravity, is one of the greatest unresolved issues in modern physics. New discoveries in quantum mechanics may offer solutions to some of the questions raised by the James Webb Space Telescope's findings. One particularly intriguing idea comes from the field of string theory, which proposes that the fundamental building blocks of the universe are not particles, but rather tiny vibrating strings of energy. According to string theory, the properties of matter and the forces governing the universe arise from the way these strings vibrate. If string theory is correct, it could provide a unified framework that explains both quantum mechanics and general relativity, offering a comprehensive understanding of the universe's origins. As these groundbreaking discoveries unfold, they push the boundaries of human understanding and inspire profound questions about the nature of the universe. The interplay between theoretical physics and observational evidence is at the heart of these developments. Each new insight challenges established paradigms, compelling scientists to rethink and refine their theories. For example, recent data from the James Webb Space Telescope suggests that galaxies formed more quickly and were more massive in the universe's infancy than previously predicted. This prompts a re-evaluation of traditional models, such as the role of cosmic inflation and the processes governing galaxy formation. In parallel, the search for a unified theory remains one of the most ambitious goals in physics. This effort seeks to reconcile quantum mechanics, which explains the universe on the smallest scales, with general relativity, which describes the behavior of large-scale cosmic structures. String theory and its offshoots, such as M-theory, offer promising avenues for bridging this gap. These frameworks suggest that our universe might exist as part of a multidimensional multiverse, with each dimension influencing the others in subtle, yet profound ways. Moreover, the exploration of black holes and their enigmatic properties continues to provide vital clues about the nature of spacetime. Black holes, with their immense gravitational pull, represent extreme conditions where the laws of physics break down. The study of phenomena such as Hawking radiation, which theorizes that black holes emit particles, offers insights into the interplay between quantum mechanics and gravity. Observations of black hole mergers, facilitated by gravitational wave detectors like LIGO and Virgo, also shed light on these cosmic mysteries. The investigation of dark matter and dark energy remains a priority. Together, these elusive components are believed to make up about 95% of the universe, yet their true nature remains unknown. Experiments such as those conducted at CERN and other particle accelerators aim to identify the particles or forces responsible for dark matter's gravitational effects. Simultaneously, researchers are developing advanced observational techniques to better understand dark energy and its role in driving the universe's accelerated expansion. Philosophical implications also loom large. If concepts such as the multiverse or a simulated universe are validated, they would challenge long-held notions of reality, existence, and humanity's place in the cosmos. These ideas invite profound ethical and metaphysical questions, such as the purpose of our universe and the possibility of intelligent creators, whether natural or artificial. As these theories gain traction, they blur the line between science and philosophy, fostering interdisciplinary dialogues that expand the scope of inquiry. Meanwhile, technological advancements in observational tools promise to unlock new frontiers of discovery. The James Webb Space Telescope is only the beginning. Upcoming missions such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission aim to map dark matter and dark energy with unprecedented precision. These instruments, coupled with artificial intelligence-driven data analysis, could uncover patterns and anomalies that reshape our understanding of cosmic evolution. The search for extraterrestrial life also takes on new urgency as scientists refine methods for detecting biosignatures in exoplanet atmospheres. Recent advancements in spectroscopy allow researchers to analyze the chemical composition of distant worlds, identifying potential markers of life such as oxygen, methane, and water vapor. The discovery of even microbial life beyond Earth would represent one of humanity's most transformative milestones, prompting a re-evaluation of our place in the cosmic order. As humanity reaches further into space, the future of exploration itself becomes a pressing topic. Initiatives like NASA's Artemis program and SpaceX's Starship missions aim to establish a human presence on the Moon and Mars, laying the groundwork for interplanetary colonization. These endeavors not only push the boundaries of engineering and science, but also raise ethical and societal questions about humanity's role as stewards of the cosmos. In the face of these monumental challenges and discoveries, collaboration across disciplines is essential. Physicists, astronomers, philosophers, and engineers must work together to tackle the complexities of the universe. Public engagement and education also play a crucial role in fostering a global sense of curiosity and investment in these endeavors. As the quest for knowledge continues, it reaffirms the boundless potential of human ingenuity and the enduring mystery of the cosmos.